Hello everyone, here we'll be discussing 2.7, which regards derivatives and rates of change. This is basically going back to what we saw at the very beginning in 2.1, where we talked about tangent and the velocity problems, where basically we'll be talking about rates of change, instantaneous rate of change, which is related to the slope of the tangent line, which we end up calling the derivative. So here let's recall the slope of the tangent line of f of x at x equals a is this, so I'm calling it m for slope. The limit as x goes to a of f of x minus f of a all over x minus a. So notice this is just the slope of the secant line from x to a, or from a to x. And then we're taking the limit as x approaches a, so that instead of a secant line at 2 points, we now have a tangent line at 1 point. So just to give the visualization, again, we have this function f, and the tangent line at this x value a, let's say this is the x value a right here, then the tangent line will look something like this in this case, and the slope of this tangent line is m. Good. Now we can modify this a little bit so that the denominator is 0, because notice when you plug in x to be a, try in for DSP, because this of course is just a limit problem now, then as x goes to a, you get a minus a in the denominator, and in fact you get f of a minus f of a in the numerator, so we end up getting 0 over 0, which is of course an indeterminate form, kind of giving us an idea that these limits should actually always exist basically, and they normally do. And this also kind of tells us why we started off with this problem, but then ventured off into a side quest, so to speak, to get a better handle on limits, so now we can talk more formally about finding slopes of tangent lines. So what we're going to do is kind of modify this expression here. If we do the substitution by letting h be equal to x minus a, notice the denominator just becomes h, okay? And also, as x approaches a, what does h approach? Well, h would approach, well, h is equal to x minus a, but as x gets closer to a, then h will get closer to a minus a, which is 0. So notice we have that here. So replacing the limit part with h goes to 0, we're replacing the denominator with h, and notice if you solve for x here to replace f of x, just add h to the other side, you get x is equal to a plus h. Perfect. So this is enough motivation to translate this expression to this new expression here, and this is what we define to be the derivative, or slope of the tangent line, denoted f prime of a. So this expression here, so ignoring the m part, so now redefining this as f prime of a, is the derivative of f of x at x equals a. Now again, slope of the tangent line is just the derivative. That's what derivative kind of means, but in a later section, in fact in the next section 2.8, we'll be talking about derivative as a more abstract object, just as a function of x. But as far as right now, we're going to see a lot of the context as far as slope of the tangent line. So here we want to find f prime of 0. So notice this really just means we want to find the slope of the tangent line of f of x at x equals 0. Of this function f of x equals x squared minus x. So I'm going to use this expression here. So notice this is going to be f prime of 0 is going to be the limit as h goes to 0 of what? So I'm just going to mimic this where a is 0 in this case. So we're going to have f of 0 plus h. Notice that's just h itself. So I'll rewrite that in a second. Minus f of a, which is 0, over h. Good. So now again, f of 0 plus h is literally just f of h in this particular case. And in fact, what's kind of funny here is that this is actually the same as f of h minus 0, f of h minus f of 0 over h minus 0. So it's literally the same expression as here, coincidentally. So it's almost like the substitution we tried to embed in this new expression doesn't really do much for this particular instance. But in any event, let's see what we can get going. So f of h is going to be h squared minus h. We're still in the limit though as h goes to 0. So it's h squared minus h minus f of 0, but notice f of 0 is 0 squared minus 0, which is 0. So I won't even write it, over h. And notice in the top, we can pull an h out. So I'll do that right here if that's okay. So pulling h out of h squared minus h just gives you h outside of h minus 1. And notice we can cancel these h's. So we only have the expression h minus 1, and then by DSP, when we plug 0 in directly into h minus 1, we get negative 1 as our answer. So f prime of 0 is equal to negative 1, and what this means is that the slope of the tangent line at x equals 0 is negative 1. We're going to basically do the same thing but with different functions, and we'll actually see 2 more examples before moving on to the next idea. Right, so for these examples here, we want to find the equation of the tangent line at the given point. And notice we can verify the point indeed satisfies this equation, or these equations. If you plug in negative 2 in for x, you get 2 minus negative 2, which is 2 plus 2 in the radical, which is square root of 4, which is indeed 2. If you plug in 1 into this, you get 3 on top and 3 on the bottom as well. 3 over 3 is 1, so the y value indeed checks out for these particular x values. Now notice we want to find the equation of the tangent line. So to do this, we need, well, the slope of the tangent line first, and then we can use point slope with the point given to find the actual equation. We actually did that in 2.1, but it was kind of hard to do in the sense that we didn't really have a great handle on limits to find the slope of the tangent line. So, yeah, again, it was a little difficult to proceed from there. But here, now that we have developed all these different tools to actually solve limits, we'll be able to do this not too difficult. So let's see. First, we need the slope. So let me just say, first step here is to find the slope, and I want to call this f prime of the x value of the point given, which is negative 2. Now, of course, in doing this, I'm going to basically assume that our function is equal to y. So I'm relabeling y as f of x, which is a better notation in the context of the formula we had for slope of the tangent line in terms of derivatives. And this, of course, is the limit as h approaches 0 of f of, well, a plus h, so negative 2 plus h, minus f of a, so f of negative 2, all over h. Now the good news here, of course, is that f of negative 2 is just 2. We established that already by plugging in negative 2 to verify that this y value is indeed the value you get when you plug in the x value. So this guy right here, that's just going to be 2. Perfect. This part is a little hard to discuss. It's not too bad, but basically we're replacing the inside of parentheses here with x in our equation. So let me just try to do it. I don't really have too much space. I'm going to have to erase a few things as we go along. But let's see. So f of negative 2 plus h, well, f of x is square root of 2 minus x, but we're not finding f of x, we're finding f of negative 2 plus h. So we're going to replace x with this quantity in parentheses. So negative 2 plus h. So again, f of x is radical 2 minus x, f of this is radical 2 minus this, and then minus 2. Perfect. Now if you distribute this negative on the inside, you'll get 2 plus 2 minus h. So this radical will be 2 plus 2, which is 4. So it's 4 minus h, minus 2 all over h. And again, we're still in the limit as h goes to 0. And I'm probably going to have to just kind of continue in this fashion. Even though we're going a little all over the board, that's fine. I'll just erase as we go along. Okay. So again, when you plug in 0 directly, you get radical 4 minus 2, which is 2 minus 2 on the top, so it's 0, over 0 on the denominator. So this is indeed a 0 over 0 indeterminate form. So what that tells us is that we can probably handle this a little bit differently by simplifying things to cancel our problem child here that gave us a 0 denominator. And of course, we know that when you have a limit involving radical expression, we will multiply top and bottom by the conjugate of the expression. So namely, we multiply top and bottom by radical 4 minus h plus 2, which is a sign change of the middle sign. So I hope that comes out on the screen, kind of, a little bit. It's okay. All right, so on the top we get a difference of squares. So the radical squared cancels a radical, and we just get 4 minus h. We've seen that before. Minus 2 squared is 4. Over, the denominator will leave factored. Perfect. And again, we're still in the limit as h goes to 0. And we know here that the 4's cancel, so kind of be a little careful because we have technically negative h over this h. So I'll kind of write that here. So we have limit as h goes to 0 of negative h over h times the quantity radical h minus 4 minus h, I meant to say, plus 2. Good. Now again, these h's now cancel multiplication-wise, or I guess division-wise. And we have negative 1 left over, which I kind of wanted to be careful by writing this step by step, otherwise we may lose the negative somehow. Great. So now by DSP, if we plug in h directly, notice we'll get negative 1 over what? We'll get negative 1 over, the denominator will be, well, let's see, it's radical 4 minus 0, which is just radical 4, so that's 2, plus 2. 2 plus 2, of course, is 4. So our slope is negative 1/4. Perfect. So the first step is to find our slope. Our slope was negative 1/4. So now I'm going to erase this and then continue to actually find the equation. Okay, perfect. So the first step to find the equation of the tangent line is to find the slope of the tangent line, which we're calling m for slope, but we know that's just the derivative evaluated at negative 2, which is the x value of the point given, f prime negative 2. And we did all that work to get negative 1/4. Perfect. Now we're going to be using point slope, which, just to remind you, is y minus the y value of a point that's given, equals the slope times x minus the x value of the point given. So in this case, the y value of our point is 2. The slope is the number we previously found, negative 1/4. The x value of our point is negative 2. So with a little bit of simplification here, this becomes y minus 2 is equal to negative 1/4 times x plus 2, just because of the double negative. Distributing this, we'll get y minus 2 is equal to negative 1/4 x minus 2 over 4, which reduces to 1/2, and then finally adding 2 to both sides simplifies to y is equal to negative 1/4 x plus, well, 2 minus 1/2 is 1.5, which as a fraction is 3 over 2. And this is our answer, finally. Perfect. So now we're going to repeat the same steps, but now for this problem here. All right, perfect. So now, again, step 1 here is to find the slope of the tangent line, which we know is the derivative evaluated at the x value. So that's f prime of 1. And here again, we're denoting y to be f of x. So notice this is just the limit as h goes to 0 of f of a plus h, which is 1, so 1 plus h, minus f of 1. But again, we know what that is. It's just the y value of our point, which is 1. So I'm going to denote that here. All over h. So now, what is f of 1 plus h? Again, that's kind of the hard part of this process. That's replacing everywhere you see an x in your expression, in your function of x, with the inside of this f here, which is 1 plus h. So, it's going to look a little crazy, but again, we're still in the limit as h goes to 0. It's all over h. We have minus 1. And now, let's see if we can figure this out. We want our first term here in our numerator to be f of 1 plus h. F of x is 2x plus 1 over x plus 2. So I'm going to write that kind of. You'll see what I mean shortly. So I have 2 times x plus 1 over x plus 2. Now notice, I said this, but every time I said an x, I actually wrote an open parentheses instead. And now we're going to fill those open parentheses with the input of f for the first term, which is 1 plus h. So filling all those in with 1 plus h, and I'll do that in red just to emphasize on what we're trying to do here. Perfect. Now this actually simplifies quite nicely. We end up, after distributing, we get, that's going to be 2 plus 2h plus 1, which is actually 2h plus 3 in the numerator. In the denominator, we just get 1 plus h plus 2, which is h plus 3. And again, this is minus 1 and then all over h. Great. So we haven't really done much, we just kind of simplified a little bit, but now notice when you plug in h to be 0, what we end up getting here is, let's see, we get, well, 0 makes these first terms go to 0, so we just get 3 over 3, which is 1. 1 minus 1 is 0 on top, and the bottom, of course, is 0. So this is indeed in determinant form, so we can hopefully simplify things a little bit here. And the kind of thing that comes to my mind, and hopefully it comes to your mind as well, is to clear the denominator in the sense that we have a fraction inside of a fraction scenario, which is known actually as a complex fraction. And we can get rid of this by multiplying top and bottom by the inside denominator h plus 3. Or another way of doing this is writing 1 as h plus 3 over h plus 3, combining the top into one fraction, and then multiplying the top fraction by the reciprocal of the denominator, which is h over 1. So its reciprocal would be 1 over h, and then multiplying across like that. But I think it's a little easier to see just multiply top and bottom by the denominator, h plus 3. And again, all this really does is clears the whole fraction within a fraction scenario we have. So basically this quantity is going to distribute amongst each of these two terms in the numerator. The first term, when you distribute this in, will cancel with the denominator and only leave you with the numerator 2h plus 3. So again, we get the limit as h goes to 0 of 2h plus 3 minus 1 times h plus 3, which is negative h plus 3, so you kind of have to be careful there. Okay, so keep that in mind. Over h times h plus 3. Now again, before we get carried away and start distributing things in the denominator at least, and the numerator will for sure distribute the negative, that's fine. But in the denominator, we don't want to, and why is that? It's because, remember that when you plug in 0 directly, you get a 0 denominator, and this h is the main culprit for that, and we're kind of hoping for cancellation of this h. And that will actually happen. So now what I'm going to do, just because I don't have too much space here, is I'm going to erase a few things, move this up, and then continue from there. Alright, so again, just to be a little detailed, I kind of left things exactly how we had it, instead of pulling a fast one on you and distributing ahead of time behind the scenes or something like that. So distributing this negative, we get negative h minus 3. So again, still in the limit, so don't forget to keep writing the limit until you've gotten rid of it by applying limit laws or something like that. We get 2h plus 3 minus h minus 3. Notice the 3's cancel. We get h times h plus 3 in the bottom still. And notice the numerator is 2h minus h, which is just h on top, over h times h plus 3. Again, still in the limit as h goes to 0. So at this point, we haven't canceled anything yet, and we still have 0 over 0. But yes, you probably noticed already, these pretty obviously cancel. And we end up with this expression, 1 over h plus 3, which again, I'll just kind of write as a little, for a little bit of detail there. And we can clearly see when h is 0, 1 over h plus 3 will tend towards 1 over 3. And this is really the end of the first step, and now we'll apply point slope and then be done with this example. Alright, so remember, point slope. Point slope is y minus the y value equals m, the slope, times x minus the x value. Again, point slope means you need a point and a slope. That's why we had to find the slope first, so we can use point slope with the slope we found and the point that was given. Again, hence the name point slope. Now the y value of this point, of course, is this x1, y1 is 1, this is 1 as well, and the slope we just found is 1/3. So this isn't too bad actually. This is just y minus 1 equals 1/3 minus 1, or 1/3 times x minus 1. Distribute the 1/3, we end up with y minus 1 is equal to 1/3 x minus 1/3. Adding 1 to both sides gives us y is equal to 1/3 x plus 2/3 actually. 1 minus 1/3 is 2/3. Great. And that's the slope of the tangent line, well, the equation of the tangent line actually. And what would be a really nice exercise for you to do is to graph these given expressions, these given curves, y equals radical 2 minus x, and y equals 2x plus 1 over x plus 2, and graph these individually. So I would graph this with this, and then you'll see that this is indeed a tangent line at this point. Similarly, I would graph this with this, and you'll see that this is indeed a tangent line at this point. And now we're going to move on and discuss a little bit about velocity, just because this section, of course, is called derivatives and rates of change. So we're actually going to find instantaneous rates of change of a particular scenario, and that'll be the end for the video for 2.7. Right, so now this problem is an example of an application of, again, derivatives, but in regards to physics. So here we suppose a ball is dropped from a height of 450 meters above the ground. The distance the ball travels after t seconds is given by the function f of t is equal to 4.9 t squared. And if you're wondering where this comes from, it basically comes from a kinematic equation from physics. And this 4.9 is actually 1/2 of gravity. And gravity in meters per second squared anyways is about 9.8. So notice half of that's 4.9. And then times the time in seconds squared, of course. And there's a little more to it, but basically it's because the initial velocity of the ball being dropped is 0. So the equation simplifies to this. Okay, good. So now we're asked, what is the velocity of the ball after 5 seconds? And then finally, how fast is the ball traveling when it hits the ground? Now, I'll be honest, the wording here is a little off from a physics perspective, but with all those technicalities aside, like for instance, this should actually say speed, not velocity, and technically this should be negative because the displacement of the ball is headed towards the ground. But anyways, we're just kind of considering positive things here and talking about it kind of more lightly, and really just observing the mathematics behind it. So to find the velocity, so velocity is rate of change, kind of like we saw before back in 2.1, and velocity at a particular instant in time, so after 5 seconds, so there's not like from 0 seconds to 5 seconds average velocity or anything like that. In this case, we want the velocity after this one time signature, so we're actually after basically instantaneous velocity, which we've discussed is the slope of the tangent line, and we know how to find that now. Really what this is asking us to find is f prime of 5. Now what we'll actually find is f prime of t. Now this idea here is something we'll explore a little more when we get to 2.8, but we're going to find the general derivative with t and then plug in t to be different things. And for a we'll plug in 5, and for b well that's to be seen. So now f prime of t is a limit as h goes to 0 of, so by the way, this is, if you want to call this velocity, we can call it v of t is equal to f prime of t. And that's limit as h goes to 0 of f of t plus h minus f of t all over h. So notice t is taking place of a in this case. Good. So again, this is limit as h goes to 0 of, well, let's see, t plus h plugged into this is 4.9 times that quantity t plus h squared, and then minus f of t is just 4.9 t squared. Perfect. All over h. All right, so I don't have too much space here, but let's see what we can get done. So notice that t plus h all squared actually expands out as t squared plus 2th plus h squared. And I've spoken of this before. Basically, it's a binomial expansion. If you multiply t plus h to t plus h and FOIL it out, you'll get the first one squared, t squared, 2 times their product, so that's 2h times 2, so it's 2th, th times 2, so 2th, and then the last one squared is h squared. And this is all multiplied, notice, by 4.9. So I'm actually going to save us a little bit of time here, and I'm going to distribute that at the same time. So multiplying this by 4.9 is 4.9 t squared. Multiplying this by 4.9 is 9.8 th. And multiplying h squared by 4.9 is plus 4.9 h squared. Perfect. And then minus that second term, 4.9 t squared. This is in the numerator all over h, and it's still in the limit as h goes to 0, and things are going to collapse really quickly right now. So notice first off, cancellation at the top. It means these go away. And what's left in the numerator, notice these two terms both have h, so we can pull it out and cancel with this. So we'll end up getting the limit as h goes to 0 of, pulling that h out, we'll get 9.8t. So that's the first term. And then 4.9h. That's the second term, and then all over h. So notice these h's cancel out like this. And then if we plug in h to be 0, the first term remains 9.8t. The second term actually goes to 0 in the limit. So really we're just left with 9.8t. And I probably shouldn't box it, but I'll underline it for sure. Now I'm going to erase a few things and collapse this back up, and then we're going to plug t to be 5 and then be done with part A. Alright, so we found out v of t is really just 9.8 times t, so that means v of 5, the velocity after 5 seconds, is 9.8 times 5, which is actually 49, and it is in meters per second as the unit there. Notice velocity, unit of velocity is time unit, distance unit I should say, divided by time unit, so that's meters per second in this case. And now finally part B asks how fast is the ball traveling when it hits the ground. So it's basically asking what is the velocity after t seconds, where t is a time signature when the distance traveled is the same as, well, the distance it's dropped from, the ball is dropped from. So we can actually find the distance by plugging in a t value. So again, it's a little hard to describe them in words the way I worded it, but we want to find v of t, where t is the time to hit ground. And notice the time to hit ground would imply that the distance traveled is 450, which we haven't actually used in this problem at all. So let's see. Well, it better be more than 5, because if it's less than 5, then that means this is when it's like through the ground or something. But that's just kind of me thinking out loud. So to find out the time it takes for this thing to hit the ground, for this ball to hit the ground, is, well, the t value, where 4.9 t squared, is equal to the distance traveled, which is 450. So basically, to solve for t, we're going to solve this equation. 450 is equal to 4.9 t squared. And that's actually not too bad to solve for. Just divide by 4.9 and then square root to get rid of the square. So divide both sides by 4.9 and then square root. So we'll get t squared is equal to whatever that decimal is. So let me do that real quick. All right, so using my calculator, I got that this fraction is about 91.8. So let me just use approximate. And now finally, to get t by itself, we're going to square root both sides to get rid of that square. And technically, when you square root both sides, you need a plus or minus. But since time here is a positive value, we'll only take the positive root. And we'll actually get that t is equal to about 9.6. And that's in seconds. Okay, good. So we actually found the time it takes for this thing to hit the ground. And now what we're going to do is find the velocity when it hits the ground by finding the velocity after this many seconds. So really what we want to find is v of 9.6. Now v of 9.6 is, well, v of t is 9.8t, so this is going to be 9.8 times this t value, which is 9.6, and using my calculator again, 9.8 times 9.6 gives me about 94.08. Let's just say 94. So it's approximately 94 meters per second. If you want to be more accurate, you can be more accurate, but that's what I'm going to say there. Anyways, that concludes our discussion for 2.7. See you in the next video for 2.8. It's going to be a lot of fun. Thanks for watching. Hope you enjoyed. See you then.